Hello everyone, this is Levi Sheridan. I hope you all had a great New Year's. I was away from the shop for a bit, but now I'm back, so I'll continue to make videos. Today, I am making a video about my ultrasonic levitator devices. So first I'm going to go into a little bit of the theory about sound and waves so y'all can understand how this works, and then I will show it working. So I hope you enjoy, and thanks for watching. Before I can explain how this ultrasonic levitation device works, we need to understand a few things about sound. Sound, for our concern, has three main fundamental properties. Frequency, also known as pitch, is the number of times per second a wave repeats itself. And for our case, it will be measured in hertz. Next, we have the wavelength, which is essentially the distance between two peaks of a wave. And it can be measured in any distance, but we will be using centimeters. Finally, we have amplitude, which is the height or power of the wave, and we will be measuring this in watts. In order for this device to work, it must produce a stationary or standing wave. A standing wave is a wave which oscillates through time, but its amplitude profile is stationary through space. What this means is, instead of the peaks or high pressure zones of the sound wave moving through space, they stay in one spot. And what this causes is there to be a line of high pressure, low pressure, high pressure, low pressure, and high pressure zones repeating. A standing wave is produced when a wave is reflected back at the source from any multiple of 1/2 of its own wavelength. This is all very complicated to explain verbally, so I am going to add some visuals that will hopefully aid in my explanation. So essentially what's happening is we are getting a vertical line of high and low pressure zones alternating all the way up from the surface of the transducer where the sound is emitted all the way up to the surface of this plate, which is hopefully placed at exactly any multiple 1/2 of the wavelength. So this transducer is a 28 kilohertz transducer, and we know that wavelength is equal to the velocity of sound divided by the frequency of the sound wave. We know that the velocity of sound is roughly 34,300 centimeters per second, and that this transducer produces 28 kilohertz sound waves. So we can plug that into the equation and figure out that the wavelength coming out of this transducer is 1.225 centimeters. If we divide that by 2, we see it's 0.6125 centimeters, and that tells us as long as this plate is any multiple of 0.6125 centimeters above this transducer surface, we should produce a standing wave in this area here. And in that standing wave, we have high and low pressure zones in which we are able to insert very light small objects, and due to the high and low pressure forces, we are able to essentially levitate small light objects in midair. I hope that explanation is all right. I hope the visuals help, but I am now gonna show you guys the device working a little bit more. So as you can see, this works well. The threaded rods and the nuts allowed me to adjust the plate up and down so that I could produce a standing wave by adjusting the plate to the proper height. And this is great. However, I thought it was a little large, so I wanted to design something that was smaller and possibly handheld. And this is what I've come up with. So this is a smaller transducer. It's a 40 hertz transducer as opposed to a 28 transducer, but they still both run on 100 watts at 110 volts. This device is consisted of its reflector plate, the transducer inside, and the transducer holder. The cool thing about this design is instead of using threaded rods and nuts to adjust the plates are already designed to be at the correct height, and you simply switch out your plate for whatever height you want. So the way that works is you just take the plate, you twist it, and lift up. And that's all it takes. And then you could theoretically design any other plate you wanted for any other transducer or any other height, and you could simply set it down and then twist it on, and it stays on really well. Here's the power board for it. I have to print a handle and put it in and then run a power cord out of it. But essentially what this is a handheld version of that. And it should allow more people to kind of get up closer and hold on to it and just have a good time seeing this. So these are my 2 designs so far. I have yet to test this one, but this one obviously works, as you can see in the video. I'm really happy with them. I hope you enjoyed and learned a little something. Thank you for watching, and thank you for your curiosity. Have a good one.